Earth is very old. Long before written language, before cities, before the first humans ever looked up at the sky, this planet was already changing, forming, erasing, and reshaping itself. Mountains rose and wore away. Oceans opened and closed. Entire worlds of life appeared, flourished, and disappeared, leaving only quiet traces behind. When we place human history next to that immense timeline, it becomes almost weightless, like a thin line drawn near the end of a very long page. For most of Earth's existence, there were no observers, no tools, no stories, no names for time or matter. And yet, the planet was never still. It moved through slow cycles of heat and cold, pressure and release, growth and collapse. The ground beneath us today contains layers formed hundreds of millions of years apart, stacked patiently one above the other. Each layer is a record written not in words but in chemistry, structure and pattern. Welcome to AstraFlow. Here, science drifts like starlight and curiosity becomes calm. Tonight, let your thoughts slow down, your breathing soften, and your mind settle into quiet understanding. As you listen, you might imagine where you are right now, perhaps in a quiet room, perhaps lying down, letting the day loosen its grip. Wherever you are resting on a planet with a memory far deeper than our own, and that memory invites a simple question, not urgent, not alarming, just gently curious. If Earth has existed for billions of years and humans for only a brief moment, what filled all that time before us? This question does not assume an answer. It does not rush toward conclusions. It simply acknowledges scale. Geological time is measured in millions of years, sometimes tens of millions. Human lifetimes, by contrast, are measured in decades. Even the entirety of recorded human civilization fits into a fraction so small that it barely registers when compared to Earth's full history. When scientists study ancient rocks, they're not looking for stories in the human sense. They look for patterns, ratios, subtle shifts in composition, a change in sediment size, a trace of an element that appears suddenly and then disappears. These are the quiet signals that survive when everything else is gone. Over time, Earth recycles almost everything on its surface. Wind breaks stone into sand. Water carries material to the sea. Plates of crust slide beneath one another, melting and reforming. Volcanic eruptions bury landscapes. Ice advances and retreats. Given enough time, even the largest structures are reduced to particles and redistributed. This means that the deep past does not preserve events in the way we might expect. It does not keep buildings, machines, or roads. It keeps chemistry. It keeps patterns written at a planetary scale. And because of that, the farther back we look, the quieter the record becomes. Still, quiet does not mean empty. The idea we are exploring tonight is not a declaration, but a possibility shaped by time itself. Not the claim that something must have existed, but the recognition that Earth's history is long enough for many things to have happened, and long enough for most of them to be erased. Now let's begin and explore the science of what it would mean if Earth had a civilization before humans. Earth formed about 4.5 billion years ago. That number is so large it can feel abstract, but in science it has very real meaning. It represents the time since our planet first cooled from a cloud of gas and dust into a solid world with a surface, oceans, and an atmosphere. Over those billions of years, Earth has not simply existed. It has changed continuously, often in ways that would feel extreme if witnessed directly. For the first several 100 million years, Earth was a violent place. Asteroids struck frequently. Volcanoes were widespread. The surface was reshaped again and again. Over time, conditions stabilized enough for liquid water to remain on the surface. Oceans formed. The atmosphere evolved. Chemistry became more complex. Eventually life appeared. What is important here is not the exact sequence of events, but their scale. Life has existed on Earth for roughly 3.8 billion years. Complex life, organisms with many cells, appeared much later, and creatures capable of building tools, controlling fire, and shaping environments intentionally arrived only very recently. Modern humans have existed for about 300,000 years. Agriculture began around 12,000 years ago. Written history covers roughly 5,000 years. Industrial civilization spans only a few hundred years. When placed against Earth's full timeline, these numbers shrink dramatically. Geologists often use visual comparisons to make this clear. If Earth's history were compressed into a single calendar year, modern humans would appear in the final hour of December 31st. All of recorded human history would fit into the last few seconds before midnight. Everything before that, oceans forming, continents drifting, mass extinctions, the rise and fall of countless species would already be over. This perspective matters because it reframes what we mean by ancient. In everyday language, ancient might mean a few thousand years old. In geology, ancient often means hundreds of millions of years. At those scales, even major events can become faint. Earth has experienced at least 5 mass extinctions, periods when a large percentage of life disappeared in a relatively short time. Entire ecosystems vanished. New ones emerged. Each time the planet recovered, but it did so differently. Life did not return to a previous state. It moved forward along a new path. Between these dramatic events were long stretches of relative stability, lasting tens or hundreds of millions of years. During those periods, climates remained consistent enough for complex systems to develop. Forests spread, oceans deepened, animals specialized. These stable windows are important because they represent the conditions under which complexity can grow. From a scientific standpoint, Earth has had many opportunities to host complex systems. Whether those systems ever included something we would call a civilization is an open question. But the time available is not small, it is immense. When we say that Earth is 4.5 billion years old, we're not just stating a number. We're acknowledging that the planet has had enough time for almost anything physically possible to occur, and enough time for most traces of those events to fade. Understanding this timescale does not require belief or speculation, it simply requires patience. And as we move deeper into this topic, that patience becomes one of our most important tools. When we talk about human history, we often imagine it as something vast and detailed. We learn timelines filled with empires, migrations, inventions, and cultural change. Compared to an individual human life, this history feels long and complex. But compared to Earth's history, it is extraordinarily brief. Modern humans have existed for roughly 300,000 years. That may sound like a long time, but for most of that period, humans lived as small groups of hunter-gatherers. There were no permanent cities, no large-scale agriculture, and no technologies capable of reshaping the planet. Human populations remained low, and their environmental impact was limited and localized. The transition to agriculture began around 12,000 years ago, after the last major ice age started to recede. This shift allowed human populations to grow, settle, and gradually form more complex societies. Even so, early civilizations were small by modern standards. Their tools were simple, their energy sources were limited to muscle, wind, water, and fire. Written language appeared only about 5,000 years ago. Everything before that exists outside of recorded history. We know about it through archaeology, genetics, and geology, not through written records. This means that the vast majority of human existence is already silent in the historical sense. Industrial civilization, the kind capable of altering global climate and chemistry, is even younger. Coal-powered industry began roughly 250 years ago. Oil and gas followed. Nuclear technology is less than a century old. Plastics, synthetic chemicals, and modern electronics are younger still. From a geological perspective, these events are almost instantaneous. A few centuries barely register in sediment layers. Even 10,000 years, the full span of agriculture, is often difficult to distinguish clearly in rock or soil records unless something very distinctive occurred. This is why geologists and earth scientists are careful when interpreting the past. The shorter an event is, the harder it is to detect after enough time has passed. Most human activity before the industrial era left no clear global signal. Only recently have our actions begun to produce changes that will remain visible far into the future. This contrast between human time and geological time creates an important insight. If our own civilization, with all its cities and infrastructure, were suddenly gone, much of it would vanish quickly. Within a few thousand years, buildings would collapse, metals would corrode, vegetation would reclaim cleared land. After a few million years, only faint chemical traces might remain. This does not mean human civilization is insignificant. It means that Earth is very good at erasing detail. The planet records only what is large, persistent, and global. Everything else fades into background noise. Recognizing how short human history is does not diminish our importance. Instead, it places us within a much larger story, one where time moves slowly and only the quietest, deepest signals endure. When scientists use the word civilization, they are not thinking about culture, art, or philosophy in the way historians often do. In earth science, the term is defined more narrowly and more carefully. A civilization, in this context, is a system capable of sustained energy use, tool-making, environmental modification, and long-term impact beyond a single generation. This definition matters because it removes ambiguity. A civilization is not simply a group of intelligent beings. It is not defined by language alone, or social organization, or creativity. It is defined by measurable interaction with the environment, interactions that leave traces. At the most basic level, a civilization requires energy. Food energy supports bodies, but technological societies rely on additional energy sources to build structures, process materials, and transport goods. Fire, wind, water, fossil fuels, electricity, and nuclear reactions are all examples of energy harnessed beyond biology. Civilizations also create tools and infrastructure. Tools amplify physical ability. Infrastructure extends influence across space and time. Roads, irrigation systems, buildings, and machines all fall into this category. These systems allow a society to grow beyond the limits of individual effort. Another key feature is environmental modification. Civilizations reshape landscapes intentionally. Forests are cleared. Rivers are redirected. Soil composition changes. Atmospheric chemistry can shift. These changes are not always dramatic, but when sustained over long periods or large areas, they become detectable. Importantly, civilization does not require advanced technology by modern standards. Even early agricultural societies altered ecosystems significantly. However, the scale of impact increases as energy use grows. The more energy a society controls, the more noticeable its footprint becomes. From a geological perspective, the most important question is not whether a civilization existed, but whether its activity was widespread and long-lasting enough to leave a signal that could survive deep time. Small, localized societies may leave almost nothing behind after millions of years. Large, energy-intensive societies are more likely to be recorded. This is why scientists focus on global markers rather than individual artifacts. A single city, even a very large one, may vanish completely. But a global change in atmospheric composition, ocean chemistry, or sediment patterns is harder to erase. Under this definition, modern human civilization clearly qualifies. We extract energy at planetary scale, we alter climate systems, We introduce new materials into the biosphere. These effects are already measurable in geological records forming today. When we ask whether Earth could have hosted a civilization before humans, we're not imagining monuments or machines waiting to be found. We're asking a quieter question. Did any system before us ever reach a level of energy use and environmental interaction large enough to leave a lasting planetary signal? This way of thinking does not assume an answer. It simply defines the terms clearly. And with those terms in place, we can begin to examine what Earth's long, layered history is actually capable of preserving. When considering the possibility of civilizations before humans, it is important to separate intelligence from technology. Intelligence appears in many forms across the natural world, long before humans ever existed. It is not a sudden or singular phenomenon. It develops gradually, shaped by survival, adaptation, and environmental pressure. Today we observe complex intelligence in many species. Birds plan ahead and use tools. Octopuses solve puzzles and show curiosity. Dolphins recognize themselves and communicate with structured signals. Great apes learn, teach, and adapt behaviors across generations. None of these species build cities or alter global climate, but they demonstrate that intelligence can emerge repeatedly under the right conditions. From an evolutionary perspective, intelligence is not rare. It is a useful trait. The ability to learn, remember, predict, and cooperate offers clear survival advantages. Over millions of years, natural selection often favours organisms that can process information more effectively than their competitors. What is rare is not intelligence itself, but a particular combination of traits. Technological civilizations require not only cognitive ability, but also physical structures that allow fine manipulation, long lifespans that permit learning and teaching, social systems that support cooperation, and environments stable enough to allow complexity to build over time. Humans happen to develop all of these features together. We have dexterous hands, high-energy diets, long childhoods for learning, and strong social bonds. We also evolved during a period of relative environmental stability, which allowed technology to accumulate rather than be repeatedly erased by catastrophe. Looking backward, it is possible that other intelligent species existed that lacked one or more of these key elements. An organism might have been highly intelligent but short-lived. Another might have lived in an environment too unstable for long-term development. Some may have lacked the physical ability to manipulate materials precisely. From a scientific standpoint, this matters because intelligence alone does not guarantee a lasting footprint. A species can think, communicate, and even plan, yet leave no detectable trace after millions of years. Intelligence does not automatically translate into planetary impact. This understanding gently narrows the question. The issue is not whether Earth could have hosted intelligent life before humans. That is very likely. The deeper question is whether any such intelligence ever crossed the threshold into sustained, energy-intensive activity that altered the planet itself. By recognizing that intelligence appears naturally and often, we avoid treating humans as an isolated anomaly. At the same time, we acknowledge that the specific pathway leading to technological civilization may be uncommon, fragile, and dependent on many factors aligning at once. This perspective encourages caution. It reminds us that absence of evidence is not evidence of absence, but also that not every form of intelligence leaves a signal that deep time can remember. Evolution has no plan and no destination. It does not work toward intelligence, technology, or civilization. Instead, it responds moment by moment to conditions in the environment. Traits that help organisms survive and reproduce tend to persist. Traits that do not gradually disappear. Over long periods of time, this process creates diversity, complexity, and sometimes surprising outcomes. Because humans are the only technological civilization we know, it is easy to assume that evolution naturally leads in our direction. From a scientific perspective, this is a misunderstanding. Humans are one possible outcome among many, not an inevitable result. If Earth's history were replayed with small changes in climate, geography, or timing, the dominant species today might look very different or might not exist at all. For most of Earth's history, life remained simple. Single-celled organisms dominated the planet for billions of years. They were extraordinarily successful. They survived extreme conditions, mass extinctions, and dramatic environmental shifts. From an evolutionary standpoint, simplicity worked very well. Complex multicellular life appeared much later, and even then it took hundreds of millions of years for large animals to become widespread. Intelligence, as we recognize it, emerged only recently and in limited forms. This suggests that intelligence is not a default outcome, but a special case. Even when intelligence does appear, it does not necessarily increase without limit. Evolution favors efficiency, not excess. Large brains consume a great deal of energy. They require long development periods and complex social support. In many environments, simpler solutions are more effective. This is why many successful species show little change over vast stretches of time. Sharks, insects, and reptiles have remained relatively stable for tens or hundreds of millions of years. They adapted just enough to persist. There was no evolutionary pressure pushing them toward tool use or technological manipulation. From this perspective, human intelligence represents a narrow evolutionary path, not a universal trend. It required a specific sequence of events: climate fluctuations that favoured adaptability, ecological niches that rewarded cooperation, and biological traits that allowed learning to accumulate across generations. Understanding this helps frame the central question calmly. If evolution does not aim towards civilization, then the existence of long pre-human eras does not automatically imply the existence of earlier civilizations. It simply means that many possibilities were explored, most of which did not lead to technology. At the same time, evolution does not forbid complex outcomes. Given enough time and the right conditions, unusual combinations can occur. Earth has had billions of years to experiment, and most of those experiments have left little behind. Recognizing that evolution is indifferent, neither guiding nor preventing, allows us to ask careful questions without expectation. We're not looking for a destiny written into nature. We're observing the quiet results of countless trials, most of which ended without lasting marks. Before modern humans appeared, Earth was already home to several human-like species. These earlier hominins were not primitive in the way they are sometimes imagined. They walked upright, used tools, controlled fire, and lived in social groups. For long stretches of time, they were successful, adaptable, and widespread. Fossil evidence shows that multiple hominin species often existed at the same time. Homo habilis, Homo erectus, Homo heidelbergensis, Neanderthals, Denisovans, and others shared the planet across hundreds of thousands of years. Some migrated across continents, some survived ice ages, some developed regional cultures with distinct tool styles. Homo erectus, for example, existed for nearly 2 million years. That is far longer than our own species has existed so far. They made stone tools, used fire, and adapted to many different environments. In evolutionary terms, they were extremely successful. Yet despite this long presence, their impact on the planet remained limited. Their populations were small. Their energy use came almost entirely from food and firewood. Their tools, while effective, were simple and biodegradable. Over time, the traces they left behind blended into natural sediment and erosion processes. From a geological perspective, this is important. Even species that look very similar to us, and that lived for long periods, did not produce global signals. Their existence is known primarily through bones and stone tools found in rare conditions where preservation occurred. This tells us something quiet but significant. A species can be intelligent, social and persistent, yet still leave almost nothing detectable after enough time has passed. Intelligence alone does not scale up into planetary change. It also reminds us that evolution experimented repeatedly with human-like forms. Modern humans were not the first upright tool-using primates. We are the last remaining branch of a larger family that once occupied much of the world. The disappearance of earlier hominins did not involve sudden global catastrophe. In most cases, it was gradual. Populations declined, environments changed, competition increased. Over time, some lineages faded while others continued. This gradual fading is exactly what geology is good at hiding. Slow transitions leave subtle traces, not sharp boundaries. Without careful study, they can disappear almost completely from the record. By looking at earlier hominins, we learn an important lesson for our broader question. Long existence does not guarantee visibility. Even a species that shaped tools, culture, and fire for hundreds of thousands of years can become almost invisible in deep time. As we continue, this lesson will help us understand why the search for any pre-human civilization must be framed in terms of scale, persistence, and planetary impact, not simply intelligence or duration. Technology, in the scientific sense, is not simply the use of tools. Many animals use tools in limited ways. What makes technology rare is its ability to accumulate, scale, and persist across generations. For that to happen, several conditions must align at the same time. First, there must be sufficient energy. Technology requires surplus energy beyond basic survival. Gathering food, staying warm, and avoiding predators already consume most available energy in natural environments. Only when a species can reliably access more energy than it needs for survival does technological complexity begin to grow. Second, there must be a way to store and transmit knowledge. Technology does not restart from zero in each generation. It builds slowly, layer by layer. This requires long lifespans, extended learning periods, and social structures that allow skills to be passed on accurately. Without this continuity, technological progress resets repeatedly. Third, the environment must be stable enough to allow accumulation. Frequent disasters, rapid climate shifts, or constant ecological pressure can prevent long-term development. Even intelligent species may never progress beyond simple tools if their surroundings demand constant adaptation just to survive. Fourth, physical capability matters. Fine manipulation of materials requires specific anatomical features. Precision shaping, fastening, and construction depend on dexterity and control. Without these traits, even advanced intelligence may never translate into complex technology. Humans happen to meet all of these conditions at once. We developed high-energy diets, cooperative social systems, long childhoods for learning, and hands capable of precise movement. We also lived during a period when Earth's climate, while variable, allowed extended windows of stability. This combination is not guaranteed to occur often. Over billions of years, Earth produced many intelligent and adaptable species, but very few that could cross this technological threshold. That rarity helps explain why the fossil record contains so little evidence of technological activity before humans. From a scientific viewpoint, this does not make technology miraculous, it makes it conditional. Technology emerges only when energy, biology, environment and time align in just the right way. Remove one element and progress slows or stops. This understanding also places human civilization in a delicate position. Our technological success depends on conditions that can change. If energy flows are disrupted or environmental stability breaks down, technological systems become fragile very quickly. When we ask whether a civilization could have existed before humans, this rarity becomes central. Even with vast time available, the conditions required are narrow. Earth had many chances but few clear opportunities, and yet, given enough time, rare events can still occur. The question remains open, not because evidence demands it, but because deep time allows possibilities that short perspectives easily overlook. Some species have dominated Earth for astonishingly long periods of time. When measured in millions of years, their success far exceeds anything humans have experienced so far. These species adapted efficiently to their environments, survived major climate shifts, and occupied ecological roles with remarkable stability. Dinosaurs are the most well-known example. They appeared roughly 230 million years ago and remain the dominant large animals on land for more than 160 million years. That span is difficult to grasp. It is more than 1,000 times longer than the duration of modern human civilization. During that time, dinosaurs diversified into countless forms. Some were small and fast, others were massive and slow. Some lived in herds, others were solitary. They occupied nearly every terrestrial niche available. In evolutionary terms, this was extraordinary success. Yet despite this long dominance, dinosaurs left no evidence of technology. There are no signs of large-scale environmental engineering, no global chemical shifts tied to their activity, no traces of sustained energy used beyond basic biological processes. This contrast is important. Longevity alone does not produce civilization. A species can thrive for tens of millions of years without ever developing complex technology. In fact, long-term stability may reduce evolutionary pressure to change. If a system works, evolution tends to conserve it. From the perspective of natural selection, dinosaurs did not need to innovate technologically. Their bodies, behaviours, and reproductive strategies were sufficient. They dominated without reshaping the planet in ways that would leave lasting geological signals. This observation helps refine our expectations. If a civilization were to exist before humans, it would not arise simply because a species lived a long time. It would require specific pressures pushing toward energy amplification, environmental control, and cumulative knowledge. Most long-lived species follow a different path. They optimize within their niche rather than expanding beyond it. They evolve slowly. They change incrementally. Their success lies in balance, not expansion. Earth's history is full of such examples. Insects have existed for over 400 million years, sharks for more than 450 million. These organisms survived multiple mass extinctions. They adapted again and again without building anything resembling civilization. This pattern suggests that civilization is not the natural endpoint of biological success. It is an unusual strategy, one that trades long-term stability for rapid expansion and control. When we place humans within this context, our situation looks less typical. We have altered Earth dramatically in a very short time. That speed is unusual in the history of life. It makes our presence visible, but also fragile. Understanding the long-lived species of the past reminds us that most of Earth's successful life forms left very little behind. They lived, adapted, and vanished quietly. And in deep time, quiet success is often the most enduring. It can be tempting to wonder why a group like the dinosaurs, with so much time and such ecological dominance, never developed anything resembling civilization. This question helps clarify what civilization requires and what it does not. Fossil evidence suggests that many dinosaurs were intelligent in limited ways. Some showed social behaviour, others may have cared for their young. Brain size relative to body mass varied across species, and some dinosaurs were likely capable of learning and adaptation. However, intelligence alone was not enough to drive technological change. One key limitation was anatomy. Dinosaurs did not possess limbs capable of fine manipulation. Building complex tools requires precise control. Grasping, rotating, fastening, and shaping materials in repeatable ways. Even with problem-solving ability, without physical structures suited for manipulation, technology cannot easily advance. Another factor was energy strategy. Dinosaurs relied entirely on biological energy, food converted directly into movement and growth. They did not develop external systems for storing or amplifying energy. Without surplus energy beyond biological needs, large-scale construction and sustained experimentation become difficult. Social structure also matters. While some dinosaurs lived in groups, there is no evidence of long-term knowledge transmission comparable to human teaching and cultural accumulation. Technology depends on learning that persists across generations with increasing precision. Without reliable transfer of complex skills, progress resets. Environmental pressure plays a role as well. Dinosaurs were successful without altering their surroundings significantly. There was no evolutionary incentive to develop agriculture, shelter building, or environmental control. Their strategy worked. Evolution rarely pushes organisms to change when existing systems are effective. From a geological perspective, this explains why dinosaurs left such a rich fossil record, but no technological one. Bones fossilize well under the right conditions. Cities do not. If dinosaurs had developed civilization-level technology, we would expect at least indirect signals, changes in sediment patterns, widespread chemical anomalies, or disruptions in ecosystems tied to sustained activity. None of these signals appear in the geological record associated with dinosaur eras. This absence does not mean dinosaurs lacked complexity. It means their complexity followed biological, not technological pathways. Understanding why dinosaurs did not build cities helps us avoid false assumptions. Long duration, large population, and ecological dominance do not automatically lead to civilization. Technology is not an inevitable outcome of success. It is one narrow route among many. This realization refines our central question. If a civilization existed before humans, it would not have arisen simply because a species lived long enough. It would have required a convergence of physical ability, energy surplus, social transmission, and environmental pressure, a convergence that appears to be rare. At the deepest level, every civilization is an energy system. Tools, buildings, transportation, communication, and industry all depend on the ability to capture energy, store it, and direct it towards specific tasks. Without sustained energy flow, complexity cannot grow or persist. Biological organisms run on food. That energy is limited by metabolism. A body can only convert so much chemical energy into motion, heat, and thought. This places a natural ceiling on what purely biological systems can accomplish. To move beyond that ceiling, a civilization must access energy outside the body. Early human societies began with fire. Fire allowed stored energy in wood to be released on demand. It provided heat, light, and protection. Later, wind and water were used to grind grain and move boats. These were small steps, but they marked an important transition. Energy was no longer limited to muscle alone. As civilizations developed, energy use expanded. Agriculture increased the amount of energy captured from sunlight through crops. Domesticated animals added more biological power. Eventually, humans learned to tap fossil fuels, energy stored over hundreds of millions of years. This single change accelerated civilization dramatically. What matters here is not the specific energy source, but the scale and persistence of use. A civilization that continuously extracts and directs large amounts of energy will inevitably affect its environment. Forests may shrink, atmospheres may change, water systems may shift. These effects accumulate over time. From a geological perspective, energy use is one of the clearest potential markers of civilization. High energy consumption tends to leave global signals. It alters carbon cycles. It changes sediment composition. It introduces materials and compounds that would not otherwise appear. This is why scientists focus on energy when thinking about civilizations before humans. A society that never moved beyond biological energy would likely leave very little behind. Even over long periods, its impact would remain local and easily erased. By contrast, any civilization capable of industry, even at a modest level, would need energy flows large enough to register in Earth's long-term records. The planet would respond quietly but persistently. Importantly, energy use does not require advanced technology by modern standards. Any sustained system that redirects natural energy on a large scale could, in principle, leave detectable traces, but the energy must be continuous and widespread, not brief or localized. This understanding helps narrow the question again. If Earth hosted a civilization before humans, it would not be defined by intelligence or longevity alone. It would be defined by energy, how much was used, how long it was used, and how broadly its effects spread. As we move forward, we'll look at how Earth records energy use and why some traces endure while others vanish almost completely. Earth is not a static archive. Unlike the Moon or Mars, our planet is active, restless, and continuously renewing itself. This constant motion is one of the defining features of Earth, and it plays a central role in what is preserved and what is erased over deep time. At the surface, wind and water slowly break rock into smaller pieces. Rain dissolves minerals, rivers carry sediment toward the sea, coastlines shift, deserts migrate, forests grow, burn, and return. Even without dramatic events, landscapes are always changing grain by grain. Beneath the surface, tectonic plates move at a pace too slow to notice in a lifetime, but powerful over millions of years. Plates collide, lifting mountain ranges. They separate, opening new oceans. They slide past one another, releasing energy as earthquakes. In some places, entire sections of Earth's crust are pushed downward, sinking back into the mantle where they melt and are recycled. Volcanism adds another layer of change. Lava flows bury older terrain. Ash settles across wide regions. New rock forms, covering what came before. Over time, these layers stack, compress, and transform, creating the geological structures scientists study today. Because of this activity, Earth is exceptionally good at erasing surface detail. Anything built on land is temporary. Given enough time, even massive features disappear. Cities crumble, roads crack, metals corrode, concrete breaks down. Eventually, all of it becomes sediment, mixed, scattered, and often indistinguishable from natural material. This process does not require catastrophe. It happens quietly and continuously. A structure does not need to be destroyed suddenly to vanish from the record. It only needs time. From a geological perspective, this means that the absence of visible ruins tells us very little about the deep past. The default outcome for surface objects is disappearance. Preservation is the exception, not the rule. What tends to survive is not shape, but signal. Broad changes in chemistry, shifts in isotope ratios, patterns repeated across continents. These are harder for Earth's recycling systems to erase completely. Even then, survival is not guaranteed. Tectonic processes can subduct entire ocean floors, removing millions of years of history. Erosion can remove entire sediment layers. Heat and pressure can alter chemical signatures, blurring their original meaning. This recycling explains why Earth's geological record is incomplete. It is not a continuous book, but a collection of fragments. Some chapters are missing, others are partially overwritten. Scientists reconstruct the story by comparing many locations, many layers, and many types of evidence. For our central question, this matters deeply. If a civilization existed far in the past, its physical structures would almost certainly be gone. Even large-scale constructions would not survive hundreds of millions of years of erosion and tectonics. What might remain are indirect traces, subtle, persistent changes that became part of Earth's long-term systems. Changes that were not tied to individual objects, but to planetary processes. Understanding Earth's recycling does not make the past more mysterious. It makes it clearer. It tells us where not to look and where careful attention is required. It reminds us that deep time does not preserve detail. it preserves patterns. As we continue, we will begin to explore what kinds of patterns Earth is capable of remembering, and why some events leave clear marks while others fade into silence. When we imagine the legacy of a civilization, it is natural to think of buildings, roads, monuments, and machines. These feel solid and permanent to us. They define modern landscapes and shape daily life. But in geological terms, cities are among the most fragile things a civilization creates. Most human structures are built on the surface, exposed to air, water, temperature changes, and biological activity. These forces work constantly. Metal rusts, stone fractures, concrete cracks and slowly reacts with water and carbon dioxide. Plants grow into small openings and pry materials apart. Microorganisms accelerate decay in ways that are invisible but persistent. If a city were suddenly abandoned, the process of breakdown would begin almost immediately. Roofs would fail within decades. Wooden structures would rot or burn. Steel would corrode. Within a few centuries, buildings would collapse into piles of debris. Within a few thousand years, those piles would be difficult to distinguish from natural rock and soil. Over longer periods, erosion would continue the work. Rivers might shift course and carry material away. Floods would redistribute debris. Wind would remove fine particles. In regions with tectonic activity, uplift and subsidence would further distort the original landscape. What once had clear shape and purpose would become scattered fragments. Burial does not guarantee preservation. While being covered by sediment can protect some materials, pressure, heat, and chemical reactions often transform them. Organic materials break down, metals oxidize, synthetic compounds may fragment or dissolve. Over millions of years, even buried structures lose their identity. This is why archaeologists rarely find intact ancient cities older than a few thousand years. Even the most famous ruins are only visible because they are young by geological standards. They exist in a narrow window between construction and complete erasure. From Earth's perspective, cities are temporary surface disturbances. They do not become part of the planet's deep memory unless they cause broader changes. A single city, no matter how large, is unlikely to leave a global signal. This understanding reshapes how scientists think about ancient civilizations. The absence of ruins does not imply absence of activity. It simply reflects the way Earth handles surface features over time. If a civilization existed millions of years ago, expecting to find buildings or machines today would be unrealistic. The planet does not preserve architecture. It preserves consequences. What survives is not form, but effect. Not walls, but changes in soil chemistry. Not roads, but altered sediment flow. Not machines, but shifts in elemental cycles. Recognizing why cities do not last helps calm the imagination. It moves the question away from hidden ruins and toward quieter evidence. The kind that Earth is capable of carrying forward across deep time. While buildings and machines fade quickly, chemistry endures. This is one of the quiet truths at the heart of geology. Earth may erase shapes and surfaces, but it remembers changes in composition far more reliably. Atoms do not forget where they have been. They move, combine, separate, and settle into new forms, but their signatures often remain. When a material is introduced into the environment, it becomes part of Earth's chemical systems. It may dissolve in water, bind to minerals, or settle into sediments. Over time, these processes distribute chemical traces across wide areas. Even when the original source is gone, the altered chemistry persists. This is why geologists rely so heavily on elemental ratios and isotopes. Certain elements exist in slightly different forms, called isotopes, which behave predictably during chemical reactions. Some processes favour one isotope over another. When that happens, a distinct pattern is created, a pattern that can survive long after the process itself has ended. For example, Volcanic eruptions leave recognizable chemical fingerprints in ash layers found thousands of kilometers away. Asteroid impacts deposit rare elements across the globe in thin layers that remain visible tens of millions of years later. These events lasted days or years, yet their chemical traces still mark Earth's history clearly. Civilizations, too, alter chemistry when they use energy and materials at scale. Mining concentrates certain elements in unusual places. Combustion releases carbon that was locked away underground. Manufacturing creates compounds that do not commonly occur in nature. Once released, these substances enter air, water, soil, and living systems. Unlike buildings, chemical changes do not need to remain intact to be detected. They only need to shift a baseline. A slight change in atmospheric composition, repeated over centuries, can leave a signal that persists in ice cores and sediments. A sustained alteration of ocean chemistry can be recorded in the shells of microscopic organisms. This is why scientists consider chemistry one of the most promising windows into Earth's deep past. It is quiet, indirect, and persistent. It does not announce itself, it waits. However, chemistry is not immune to change. Over very long periods, heat, pressure, and biological activity can blur or overwrite signals. Elements can be redistributed. Isotopic ratios can drift. Interpretation becomes more difficult the farther back we look. Still, compared to physical structures, chemistry has a remarkable ability to endure. It does not preserve stories, but it preserves consequences. It does not show us who acted, but it shows us that something happened. For our central question, this distinction is crucial. If any civilization existed long before humans, its most likely legacy would not be ruins or artifacts. It would be a subtle, global chemical imprint, one that became woven into Earth's natural cycles. Understanding this allows us to look for the right kind of evidence, not dramatic remains, but quiet shifts, not objects, but patterns. And as we continue, we will explore how scientists search for these patterns and what they have already found. The geological record is selective. It does not preserve everything equally, and it never has. Instead, it favours certain kinds of information, the kinds that are widespread, repetitive, and deeply integrated into Earth's systems. Understanding what the record preserves best helps clarify both what we can know about the deep past and what will likely remain unknown. The most reliable records are those formed slowly and continuously. Sedimentary rocks, for example, build up layer by layer as particles settle out of water or air. Each layer captures a snapshot of conditions at the time it formed: the temperature, the chemistry, the presence of certain organisms. Over millions of years, these layers stack into long, quiet archives. Ocean sediments are especially valuable. The seafloor accumulates material steadily over vast areas. Tiny shells from microorganisms sink and settle, carrying chemical information about the water they lived in. Dust from distant continents drifts down. Volcanic ash spreads and falls. Together, these materials create a nearly continuous record stretching far into the past. Ice cores provide another kind of preservation. In polar regions, snow falls year after year and compresses into ice, trapping tiny bubbles of ancient air. These bubbles preserve direct samples of past atmospheres, their composition, their greenhouse gas levels, even traces of distant fires or eruptions. Although ice cores do not extend back as far as rock records, they are incredibly precise. Fossils represent a different kind of preservation. They are rare because fossilization requires specific conditions: rapid burial, low oxygen, and minimal disturbance. When those conditions occur, bones, shells, and imprints can survive for immense spans of time. But most organisms leave no fossils at all. The fossil record is rich in information, but incomplete by nature. What the geological record does not preserve well are short-lived, localized events. A brief construction project, a single city, or a small population can vanish without a trace. even dramatic events may leave little behind if they are geographically limited or chemically subtle. This selectivity matters when considering ancient civilizations. Only activities that were global or sustained for long periods would have a chance of being recorded clearly. A civilization that existed briefly or that used materials similar to natural ones might blend into the background. From a scientific standpoint, this does not imply hidden histories. It simply reflects how Earth works. The planet records what is repeated and widespread. It forgets what is rare and local. By focusing on what the geological record preserves best, long-term chemical trends, global sediment layers, and large-scale disruptions, scientists narrow their search to signals that could realistically survive deep time. This perspective brings a sense of calm. It reminds us that uncertainty is expected. It also reminds us that the absence of obvious evidence is not mysterious. It is the normal outcome of a planet that is constantly changing. As we move forward, we will look at moments in Earth's history where the geological record becomes especially clear, times when something brief still left a lasting mark. When scientists study Earth's deep past, they rarely rely on a single location or a single sample. Instead, they read the planet the way one might read a very old, partially damaged book, by comparing many copies of the same page scattered across the world. Sedimentary rock layers form when material settles over time. Each layer represents a period when conditions were relatively stable. Changes between layers often indicate shifts in environment, a new climate, a rising or falling sea level, increased volcanic activity, or changes in life itself. By examining the order and composition of these layers, scientists can reconstruct sequences of events that occurred millions of years ago. One of the most important principles in geology is superposition. In undisturbed sedimentary rock, older layers lie beneath younger ones. This simple rule allows scientists to place events in relative order, even before precise dating is applied. Absolute dating methods, such as radiometric techniques, then provide age estimates by measuring the decay of radioactive elements. Beyond age, rock layers contain chemical information. The presence of certain elements, minerals, or isotopic ratios can reveal temperature, oxygen levels, and biological activity at the time the layer formed. For example, changes in carbon isotopes can indicate shifts in global carbon cycling, often tied to climate change or large biological transitions. Rock layers also record sudden events. A volcanic eruption may leave a thin layer of ash spread across wide regions. An asteroid impact can deposit rare elements globally in a narrow band. These layers stand out because they appear at the same relative position in rock sequences around the world, acting as time markers that connect distant locations. By aligning these markers, scientists create a global timeline. This method allows them to see whether changes were local or planetary. A signal found in one place might be regional. A signal found everywhere suggests something much larger. Importantly, interpretation is cautious. A single anomaly is rarely enough to draw conclusions. Scientists look for patterns that repeat across many sites and many types of evidence. Chemistry is compared with fossil data. Sediments are compared with ice cores. Models are tested against observations. This careful reading explains why science often moves slowly. The deeper the time period, the more fragmentary the record becomes and the more restraint is required. Ambiguity is expected, certainty is rare. For our question, this method matters. If a civilization existed long before humans, its traces would need to appear as consistent global patterns across many rock layers and regions. Isolated anomalies would not be enough. Understanding how scientists read ancient rock layers grounds the discussion. It shows that deep time is not unknowable, but it is subtle. The planet speaks quietly, and only patient listening reveals what it has to say. About 65 million years ago, something extraordinary happened. A large asteroid struck Earth, colliding with the planet at immense speed and releasing energy far beyond anything produced by natural processes on the surface today. This single event marked the end of the age of dinosaurs and reshaped life on Earth. What makes this event especially important is not just its impact, but how clearly it appears in the geological record. Across the world, scientists find a thin layer of sediment dating to the same moment in time. Within that layer is an unusually high concentration of iridium, a metal that is rare in Earth's crust but common in asteroids. This iridium layer is found on every continent. The asteroid's physical crater is also preserved. Beneath the Yucatan Peninsula lies the Chicxulub crater, a vast structure buried under sediment, perfectly matching the age and energy of the extinction event. Together, these clues form a consistent picture, a brief moment in time that left a permanent planetary signal. What is striking is how short the event was. The asteroid impact lasted seconds. The immediate devastation unfolded over hours and days. Climate effects extended over years. And yet 65 million years later, the evidence remains clear and unmistakable. This tells us something important about Earth's memory. Even extremely brief events can leave long-lasting traces if they are energetic enough and global enough. The planet does not need time alone to remember, it needs scale. For scientists, this impact became a reference point. It showed that Earth can preserve signals from sudden disruptions with remarkable fidelity. A thin layer of rock, only centimeters thick, can carry information across tens of millions of years. This realization quietly changed how researchers think about other past events. If a single day in Earth's history can be identified so clearly, then any process that alters the planet at a similar scale, even over a short time, has the potential to leave detectable traces. This does not imply that all large events are preserved equally. Many are blurred or partially erased, but it demonstrates a key principle. Earth is capable of remembering dramatic change. As we continue, this principle becomes central. The asteroid impact provides a baseline, a way to ask careful questions about what kinds of activity are loud enough, in geological terms, to be heard across deep time. After the discovery of the asteroid impact layer, scientists began to reflect on what it revealed about Earth's ability to record history. The realization was simple but profound. If a single, brief event could leave a clear, global signal that persisted for tens of millions of years, then the planet was capable of remembering more than previously assumed. This led to a quiet question, one that does not demand an answer but invites careful thought. If a momentary catastrophe could be preserved so clearly, what would happen if a process unfolded more slowly, over centuries or thousands of years, yet affected the planet just as broadly? Civilizations, if they exist at sufficient scale, operate very differently from asteroids. They do not strike suddenly. They build, expand, and persist. They extract energy day after day. They alter landscapes gradually. Their effects accumulate rather than explode. From a geological perspective, this accumulation matters. A civilization that changes atmospheric composition, ocean chemistry, or sediment patterns over long periods might leave a signal comparable in strength to a sudden impact, not because it is violent, but because it is sustained. This comparison does not suggest that civilizations and asteroids are equivalent. It simply highlights a shared property, global reach. Earth's geological record responds most clearly to changes that affect the planet as a whole, regardless of whether those changes occur suddenly or slowly. The question, then, becomes more focused and more restrained. Not whether a civilization could hide from geology, but whether any activity, biological, technological, or otherwise, ever operated at a scale large enough to be recorded in the same quiet way the asteroid was recorded. Importantly, this question does not assume that such evidence exists. It acknowledges uncertainty. It respects the limits of what is known. It also respects the limits of what can be preserved. Scientists approach this question without urgency. There is no need to rush toward conclusions. The geological record is patient. It reveals information slowly, layer by layer, as methods improve and new data emerges. By framing the question calmly, researchers avoid speculation and focus on mechanism. What kinds of processes leave lasting traces? How strong must a signal be? How long must it persist? These are questions geology is well suited to explore. As we continue, we will look at one specific idea that emerged from this line of thinking. Not as a claim, but as a structured way of asking how a past civilization, if it existed, might be detected. When scientists consider how to detect past activity in Earth's deep history, they rely on the concept of signatures. A signature is not an object or a structure. It is a pattern, a measurable change that stands out from natural background processes and persists long enough to be recorded. In astronomy, researchers search for technological signatures, or technosignatures, to identify distant civilizations. These might include unusual atmospheric gases, artificial light, or structured radio signals. On Earth, the same logic can be applied more quietly and carefully, using geology instead of telescopes. A technological signature on Earth would not announce itself. It would blend into natural records, detectable only through careful analysis. It might appear as a shift in elemental ratios, an unexpected chemical compound, or a sudden change in sediment composition that does not match known natural causes. One example is atmospheric alteration. When large amounts of energy are used, especially through combustion, gases are released. Carbon dioxide, methane, and other compounds accumulate. Over time, these changes can be preserved in ice cores, sediments, and even fossilized biological material. Another possible signature is material redistribution. Mining concentrates elements that are normally spread thinly through rock. Manufacturing can create materials or molecular structures that rarely form on their own. When these substances enter soil and water, they become part of Earth's chemical cycles. Waste is also a signature. Every complex system produces byproducts. Some break down quickly, others persist. Even when broken apart, they may leave fragments or altered chemistry that can be traced long after their original form is gone. What matters most is scale. Small, local activities disappear into noise. Large, sustained activities create patterns that stand out statistically. Geology is especially good at detecting such patterns because it integrates information across wide areas and long periods. This framework allows scientists to ask structured questions without speculation. If a civilization existed before humans, what kind of energy would it need? What byproducts would it create? How would those byproducts interact with Earth's systems? Importantly, this approach does not assume that any such signatures must exist. It simply defines what they would look like if they did. This keeps the discussion grounded and testable. By focusing on signatures rather than stories, science remains calm and methodical. It avoids imagining lost cities or advanced machines. Instead, it listens for subtle, persistent signals written into the planet itself. As we continue, we will turn our attention to a technological signature that we know very well, the one modern humans are creating right now. We do not need to imagine what a technological signature looks like. We're producing one ourselves, quietly and continuously every day. Modern human civilization is altering Earth in ways that are already becoming part of the geological record. One of the clearest examples is atmospheric change. Since the beginning of the industrial era, humans have released large amounts of carbon dioxide and other greenhouse gases into the air. This carbon comes from fossil fuels, material that was buried underground for millions of years. When it is released, it carries a distinct chemical fingerprint. That fingerprint can be measured. It appears in the ratio of carbon isotopes in the atmosphere, in ocean sediments, and in the shells of microscopic marine organisms. These changes are not subtle, they are global, and they are happening fast. Plastics provide another example. Synthetic polymers did not exist in nature before the last century. Today, microscopic plastic particles are found in soils, rivers, oceans, deep-sea sediments, and polar ice. Over time, these particles become mixed into sediment layers that will harden into rock. Radioactive materials form yet another signature. Nuclear weapons testing and nuclear energy production have released isotopes that do not normally occur in nature, or that appear only in extremely small amounts. These isotopes will remain detectable for thousands to hundreds of thousands of years, embedded in sediments and ice. Even changes in land use leave long-term traces. Agriculture alters soil composition. Urbanization redistributes minerals and metals. Dams change sediment flow in rivers, reshaping coastlines and deltas. These effects accumulate, becoming part of Earth's stratigraphy. What is important here is not judgment, but recognition. Human civilization has crossed the threshold of planetary impact. Our activities are no longer local or temporary. They are global and persistent. From the perspective of a future geologist, millions of years from now, our era will likely appear as a distinct layer, thin but unmistakable. A brief interval marked by sudden chemical shifts, new materials, and altered biological patterns. This realization grounds the earlier discussion. It shows that technological signatures are not hypothetical. They are real, measurable, and already forming. Earth is recording us right now. With this understanding, scientists can ask the next question calmly and precisely. If our civilization leaves such a clear signal, could any similar signal exist deeper in Earth's past, even if it is faint, altered, or partially erased? As scientists began to recognize the scale of human impact on Earth, a new term emerged to describe it: the Anthropocene. This word refers to a proposed geological epoch defined by human activity, a period in which one species became a dominant force shaping the planet's systems. In geology, an epoch is not declared lightly. It must be marked by clear, global signals that appear consistently in rock, sediment, or ice. These signals must be distinct from what came before and persist long enough to be recognized far into the future. The Anthropocene meets many of these criteria. The proposed markers are quiet, but unmistakable. A sharp rise in greenhouse gases recorded in ice cores, the sudden appearance of synthetic materials like plastics and sediments, radioactive isotopes from nuclear testing distributed across the globe, rapid changes in biodiversity, visible in fossil records as shifts in species distribution and extinction rates. What makes these markers significant is not their drama, but their clarity. They appear almost simultaneously across continents and oceans. They are not local accidents. They are the result of sustained planet-wide activity. From a future perspective, this layer will stand out sharply. It will mark a moment when Earth's chemistry and biology changed faster than at almost any other time outside of major catastrophes. The duration may be brief, perhaps only a few thousand years, but the signal will be strong. This understanding reinforces a key idea. A civilization does not need to last millions of years to be recorded. It only needs to alter Earth's systems at sufficient scale. The Anthropocene demonstrates that even a short-lived technological phase can leave a long-lasting imprint. At the same time, the Anthropocene highlights how unusual such moments are. Earth's history contains many changes, but few that occur so rapidly and so globally without an external trigger like an asteroid or massive volcanism. This raises a calm and careful question. If a similar layer existed deep in Earth's past, altered, compressed, or partially erased, would we recognize it for what it was? Or would it blend into natural variation, interpreted through familiar explanations? The Anthropocene does not answer this question, but it provides a reference point. It shows us what a technological layer looks like while it is still forming, and that perspective quietly reshapes how scientists think about Earth's long, complex memory. When scientists examine Earth's deep past, they do so with the knowledge that most signals weaken with time. Layers compress, chemistry diffuses, heat and pressure alter original conditions. What begins as a sharp boundary can become blurred, thinned, or partially erased after millions of years. This is why subtlety matters. The Anthropocene appears clear to us now because it is new. Its signals are sharp, fresh, and well documented. But if we project that layer forward hundreds of millions of years, its clarity would almost certainly fade. Plastics would fragment and disperse. Radioactive isotopes would decay. Atmospheric signals would be mixed and diluted by natural cycles. This leads to a careful consideration. A technological signature does not need to disappear entirely to become difficult to interpret. It only needs to lose contrast with background processes. When that happens, the signal may still exist, but its meaning becomes uncertain. Different technologies could also leave different kinds of traces. Not all civilizations would rely on the same materials or energy sources. A society that used mostly biological materials, renewable energy, or closed-loop systems might produce fewer long-lasting chemical anomalies. Its footprint could be quieter than our own. Even for human civilization, some impacts are subtle. Soil chemistry changes slowly. Ocean acidification is gradual. Biodiversity loss unfolds over centuries. These processes leave records, but they do not always form sharp boundaries. They require careful statistical analysis to detect. From a geological standpoint, this means that older technological signatures, if they existed, might not stand out as dramatic events. They could appear as mild deviations, slight isotope shifts, short-lived anomalies that align imperfectly across locations. This possibility does not imply hidden histories. It simply reflects how Earth works. Deep time smooths extremes, it blends edges, it turns sharp moments into gradients. Because of this, scientists are cautious. They do not expect to find clear, unambiguous markers of past civilizations, unless those civilizations altered the planet as forcefully as major natural catastrophes. More modest activity would likely be absorbed into natural variation. This understanding shapes how questions are asked. Instead of searching for unmistakable proof, researchers ask whether certain patterns are consistent with known natural processes, or whether they stretch those explanations slightly. As we continue, we will explore why the absence of clear evidence is not surprising, and why uncertainty itself is a natural outcome when looking this far back in time. When we look far into Earth's past, uncertainty is not a failure of science, it is the expected condition. Deep time does not preserve information evenly, and it rarely preserves it completely. This is why the absence of clear evidence for ancient civilizations is not surprising. Most events in Earth's history leave no trace that we can recognize today. Entire ecosystems have come and gone without leaving fossils. Long periods of stable climate leave few distinctive markers. Even major biological transitions can be difficult to detect unless they alter chemistry or sedimentation in a dramatic way. This means that the geological record is biased toward extremes. It preserves mass extinctions, large impacts, and global chemical disruptions more readily than slow, moderate processes. Anything that does not strongly disturb planetary systems is likely to fade into the background. Civilizations, if they existed before humans, would face this same filter. Unless their activity was intense, global, and sustained, the planet would quietly erase most of their traces. Over millions of years, even significant changes could be smoothed out or reinterpreted as natural variation. There is also a practical limitation. We do not have access to all of Earth's past. Much of the planet's oldest crust has been recycled through plate tectonics. Ocean floors older than about 200 million years are rare, having been subducted back into the mantle. Entire chapters of history are simply gone. What remains is fragmentary. Scientists work with incomplete data sets, unevenly distributed across time and space. This is why geology relies on probability rather than certainty. Conclusions are based on convergence of evidence, not on single discoveries. From this perspective, the lack of evidence for pre-human civilizations does not rule them out. It simply reflects the difficulty of detecting brief, complex activity across immense spans of time. At the same time, it also means that science cannot assume such civilizations existed without strong, consistent signals. This balance is important. Science remains open without becoming speculative. It acknowledges possibility without asserting belief. It accepts that some questions may remain unanswered, not because answers are hidden, but because the record itself is incomplete. Recognizing this helps calm the imagination. It removes the need for hidden ruins or dramatic revelations. Instead, it places uncertainty where it belongs, as a natural outcome of studying a planet that has been reshaping itself for billions of years. As we move forward, we will examine specific gaps and transitions in Earth's history that often attract attention, and see how scientists interpret them carefully and conservatively. When people imagine the deep past, they often picture fossils, bones turned to stone, shells preserved in rock. Impressions of leaves and footprints, fossils feel like durable records, and in some ways they are. But even fossils represent a small and selective fraction of what once lived. Technology, by contrast, is far less likely to survive. Fossilization requires very specific conditions. An organism must be buried quickly, protected from oxygen, and remain undisturbed long enough for minerals to replace organic material. Most living things do not meet these conditions. They decay, are consumed, or are scattered. Only a tiny percentage become fossils. Even so, biological materials have an advantage. Bones, shells, and teeth contain minerals that readily integrate into sediment. Over time, they can be preserved as stone replicas. This is why we can reconstruct ancient ecosystems despite the rarity of fossilization. Technology lacks this advantage. Most tools and structures are made from materials that break down quickly or react chemically with their surroundings. Wood rots, metals corrode, plastics fragment. Even stone tools, which survive better than many materials, are easily mistaken for natural rock unless found in clear archaeological context. Large technological systems are especially vulnerable. Buildings are exposed to weather, roads crack and erode, machinery rusts and collapses. Without maintenance, complex systems fail rapidly. Over thousands of years, their components become unrecognizable. Over millions of years, they are almost certainly gone. From a geological perspective, technology does not fossilize in the way organisms do. It leaves indirect traces instead. Changes in soil composition, unusual concentrations of elements, altered sediment patterns. These effects are spread thinly across the landscape, not concentrated into identifiable objects. This explains why earlier hominin technology is known mostly through stone tools. Stone is durable, and even then, such tools are found only in limited contexts. Everything else those societies used, wood, fibre, plant material, has vanished. If a pre-human civilization existed far in the past, its technology would face even harsher conditions. Time would magnify every erasing process. Tectonics would remove entire regions. Erosion would scatter remains. Chemical reactions would dissolve or transform materials. Understanding this difference between fossils and technology is important. It prevents false expectations. We should not expect to find machines or cities preserved in ancient rock. Their absence tells us very little. Instead, scientists focus on broader signals, the kinds of changes that technology might impose on Earth's systems as a whole. Fossils show us life, chemistry shows us activity. Together they provide the most reliable window into deep time. As we continue, we will look at moments in Earth's history where life and environment changed rapidly, and explore how scientists distinguish natural transitions from other possibilities. When scientists reconstruct Earth's long history, they notice that change does not always happen slowly. Much of the time, environments shift gradually, allowing life to adapt step by step. But there are also moments when change appears sudden, sharp transitions that stand out clearly in the geological record. These moments are visible as boundaries in rock layers. On one side of the boundary, conditions are relatively stable. On the other, something has shifted. Species disappear, new forms appear, chemistry changes, climate reorganizes. In geological terms, these transitions can occur very quickly, sometimes within thousands of years or less. Mass extinctions are the most dramatic examples. Earth has experienced at least 5 major extinction events, during which a large percentage of species vanished in a relatively short time. These events reshaped ecosystems globally. After each one, life recovered, but never in the same way as before. Not all sudden changes involve extinctions. Some periods show rapid climate warming or cooling. Others show abrupt shifts in ocean chemistry or atmospheric composition. In some cases, biological complexity increases sharply, with new forms appearing over relatively short spans of time. What makes these moments scientifically interesting is not their drama, but their clarity. They leave strong signals. Isotope ratios change, sediment types shift, fossil assemblages reorganize. These signals are easier to detect than slow, gradual trends. However, sudden does not mean mysterious. In most cases, scientists can identify plausible natural causes. Large volcanic eruptions can alter climate and chemistry. Asteroid impacts can disrupt ecosystems instantly. Changes in ocean circulation can trigger cascading effects. At the same time, these rapid transitions remind us that Earth systems can move quickly under the right conditions. Feedback loops amplify small changes. Thresholds are crossed. Stability gives way to reorganization. For the question we're exploring, this matters in a subtle way. If a civilization existed before humans and affected Earth at a large scale, its impact might resemble these rapid transitions, not because it was catastrophic, but because sustained activity can push systems past tipping points. This does not imply that sudden changes are evidence of civilization. Natural explanations are usually sufficient and preferred, but it does show why scientists pay close attention to sharp boundaries in the geological record. These are moments when something important happened. As we continue, we will look more closely at how scientists distinguish natural causes from other possibilities, and why careful restraint is essential when interpreting Earth's most dramatic transitions. Earth does not need intelligence or intention to produce sudden, powerful change. The planet's natural systems are capable of extreme events all on their own, driven by physics, chemistry, and feedback loops that operate over vast scales. Volcanism is one of the clearest examples. Large volcanic provinces have released enormous volumes of lava and gas over relatively short periods of geological time. These eruptions can cover millions of square kilometers, inject carbon dioxide and sulfur into the atmosphere, and alter climate for thousands of years. Several mass extinctions are closely associated with such volcanic episodes. Asteroid impacts provide another mechanism. Though rare, they deliver immense energy in seconds, triggering fires, tsunamis, atmospheric dust clouds, and long-term climate disruption. The geological record shows that these events leave clear, global markers, but they arise entirely from natural celestial dynamics. Earth's climate system itself can shift abruptly. Ice sheets grow and collapse. Ocean circulation patterns reorganize. Methane trapped in sediments can be released rapidly under warming conditions. These processes can amplify each other, producing rapid transitions that appear sudden in the rock record. Biology also plays a role. The evolution of photosynthesis dramatically altered Earth's atmosphere billions of years ago, increasing oxygen levels and transforming global chemistry. This change was driven not by technology, but by microscopic life responding to energy opportunities. These examples remind scientists to remain grounded. Nature is fully capable of creating the kinds of signals that might otherwise be mistaken for intentional activity. Sudden carbon shifts, mass die-offs, and climate disruptions do not require civilizations to explain them. Because of this, scientific interpretation always favours natural mechanisms first. When multiple natural explanations exist, they are tested rigorously before more speculative ideas are considered. This is not skepticism for its own sake, but a recognition of Earth's inherent power. For our central question, this understanding sets an important boundary. Any proposal involving past civilizations must contend with the fact that natural processes can produce dramatic, global effects without purpose or planning. This does not close the discussion. Instead, it clarifies it. The challenge is not to find unusual signals, but to determine whether those signals exceed what natural systems are known to produce. By appreciating how dramatic Earth can be on its own, scientists maintain balance. They listen carefully to the planet's record, without assuming intention where nature alone is sufficient. When scientists explore Earth's deepest history, caution is not a limitation, it is a necessity. The farther back we look, the less complete the record becomes, and the easier it is to mistake coincidence for cause. This is why scientific thinking moves slowly, especially when questions touch the edges of what can be known. Geology does not provide clear narratives, it offers fragments, layers, ratios, distributions. These fragments must be interpreted, and interpretation always carries uncertainty. A chemical anomaly might have multiple explanations. A sudden change in fossils might reflect preservation bias rather than real disappearance. A gap in the record might mean erosion, not absence. Because of this, science relies on convergence. A single line of evidence is rarely enough. Strong conclusions emerge only when multiple independent signals point in the same direction. Chemistry aligning with fossils, timing aligning across continents, models matching observations. This is especially important when considering ideas like past civilizations. Such ideas sit outside ordinary experience and can easily drift into speculation. To avoid this, scientists frame questions in terms of mechanisms rather than stories. They ask what processes are possible, what signatures would result, and whether those signatures are actually present. Care also protects against human bias. Humans are pattern-seeking by nature. We tend to connect dots, even when the connections are not real. In deep-time research, this tendency must be resisted. Apparent patterns must be tested statistically, compared globally, and evaluated against known natural processes. Another reason for caution is that scientific knowledge changes. New dating methods, new instruments, and new data can revise earlier interpretations. Conclusions must remain flexible, open to refinement rather than fixed belief. This careful approach does not mean science dismisses unusual questions. It means those questions are held gently. They are explored without urgency, without expectation, and without the need for definitive answers. In the context of this discussion, scientific caution keeps the conversation calm. It allows us to acknowledge that Earth's history is vast and complex, while also respecting the limits of what evidence can support. As we move forward, this restraint will guide the remaining sections. The focus will shift gradually from mechanisms and records toward perspective, how these ideas change the way we see time, life, and our own place within Earth's long story. Within this careful scientific framework, one idea has been proposed not as a claim, but as a structured question. It is known as the Silurian hypothesis. Despite its name, it is not a theory in the traditional sense, and it does not assert that a civilization existed before humans. Instead, it asks something much quieter. If an industrial civilization had existed on Earth long before humans, how would we know? The purpose of this thought experiment is methodological. It does not search for hidden histories, it tests the limits of detection. It asks scientists to consider what kinds of evidence could survive deep time and which kinds almost certainly could not. By framing the question this way, the hypothesis avoids speculation. It does not assume intelligence, technology, or intent. It simply explores whether Earth's geological record is capable of preserving the signatures of industrial activity at all, given enough time. This approach turns the focus inward. Rather than looking for unknown civilizations, it examines our own. What traces are we leaving? How durable are they? Which signals will still be visible after tens of millions of years, and which will fade completely? In doing so, the Silurian hypothesis becomes a tool for understanding Earth's memory. It highlights the filters imposed by erosion, tectonics, chemistry, and biological recycling. It reminds us that even large-scale activity can become subtle with time. Importantly, the hypothesis does not challenge established geology. It works within it. It accepts that natural explanations account for known events. Its value lies in sharpening questions, not in providing answers. By asking how we would recognize a past civilization, scientists learn more about how to recognize our own impact in the future. The exercise strengthens our understanding of planetary processes and the longevity of environmental change. As a result, the Silurian hypothesis occupies a calm space in scientific thinking. It is neither confirmation nor denial. It is a lens, one that helps clarify what Earth can remember and what it quietly lets go. If we imagine detection as a scientific challenge rather than a search for confirmation, the requirements become clearer and more restrained. Detecting any past civilization would not depend on finding artifacts or structures. It would depend on identifying signals that meet very specific conditions. First, the signal would need to be global or nearly global. Local activity is easily erased or reinterpreted. Only changes that spread across continents and oceans have a chance of standing out against Earth's natural variability. This is why scientists focus on atmospheric chemistry, ocean composition, and sediment layers rather than individual sites. Second, the signal would need to be persistent. Brief disturbances fade quickly unless they are extremely energetic. Sustained activity, repeated year after year, is far more likely to alter baseline conditions. Long-term shifts in carbon cycling, nutrient distribution, or isotope ratios are examples of changes that can endure. Third, the signal would need to be distinguishable from known natural processes. Earth produces many dramatic effects on its own, so any proposed signature would have to exceed what volcanism, impacts, climate feedbacks, or biological evolution can reasonably explain. This is a high standard, and intentionally so. Fourth, the signal would need to appear consistently across independent records. A genuine planetary scale change should show up in multiple environments, in marine sediments, in terrestrial rocks, and in biological remains. Agreement across these records increases confidence and reduces the chance of misinterpretation. Finally, detection would require context. A chemical anomaly alone is not enough. Scientists would need to understand when it occurred, how long it lasted, and what else was happening at the time. Patterns matter more than isolated measurements. When these requirements are applied, the challenge becomes apparent. Earth's deep past offers only a few windows where such detection is even possible. Many intervals are poorly preserved or missing entirely. Others are dominated by strong natural signals that overwhelm subtler effects. This is why the search remains theoretical. It is not that scientists expect to find evidence and have not looked hard enough. It is that the conditions for detection are rare, and the filters of time are strong. Understanding what detection would require brings the discussion back to calm ground. It shows that the question is not whether scientists are overlooking obvious clues, but whether the planet itself is capable of preserving them in the first place. When all of these requirements are applied, the current picture becomes clearer. Scientists have examined Earth's history in extraordinary detail using chemistry, fossils, sedimentology, and modelling. What they have found is a planet shaped by powerful natural processes, impacts, volcanism, climate shifts, and biological evolution, acting over immense spans of time. What they have not found is unambiguous evidence of a pre-human technological civilization. There are no confirmed global chemical signatures that require industrial activity to explain them. There are no isotope patterns that clearly exceed known natural mechanisms. There are no consistent planet-wide anomalies that align in timing, scale, and duration in a way that demands a technological cause. This absence is meaningful, but it must be interpreted carefully. It does not mean that science has ruled out all possibilities. It means that, given the data we have, natural explanations remain sufficient. Where uncertainty exists, it lies within the expected limits of incomplete preservation and complex planetary systems. At the same time, scientists are aware of what they do not have. Large portions of Earth's earliest history are missing. Ocean crust older than a few 100 million years has mostly been recycled. Some sedimentary records are fragmented or altered. Certain intervals are difficult to study because the signals are weak or overwritten. This creates a quiet tension. On one side, there is strong evidence that natural processes can account for what we observe. On the other, there is an acknowledgement that the record is incomplete and that some forms of activity, especially brief or subtle ones, could escape detection. Science holds both realities at once. It does not rush to fill gaps with speculation. It also does not claim perfect knowledge. Instead, it works with what is available, improving resolution slowly as methods advance. This balance is important. It prevents the discussion from becoming dismissive or sensational. It allows us to say, calmly and accurately, that no evidence currently requires the existence of a pre-human civilization, while also recognizing the profound depth and complexity of Earth's past. With this understanding in place, the focus can now widen. Rather than asking what we might have missed, we can ask what this perspective teaches us about time, life, and our own moment within Earth's long story. Sometimes the most important feature of a record is what it does not contain. In geology, silence is not empty. It carries information of its own. When scientists examine Earth's rock layers and find no clear signal of technological activity, that absence helps define the boundaries of what likely occurred. Silence in the geological record suggests limits. It suggests that if any complex systems existed before humans, they did not reach a scale or duration that forced the planet to remember them clearly. Earth's processes continued without being pushed far from their natural ranges. This kind of silence is consistent with what we know about Earth. Most of the planet's history unfolded without large, sustained disturbances. Life adapted within constraints. Energy flowed through ecosystems without overwhelming them. Even dramatic events were rare and often separated by tens of millions of years. The rocks reflect this stability. Long stretches show gradual change rather than abrupt disruption. Chemical cycles fluctuate within predictable bounds. Sediments accumulate steadily. Fossil assemblages shift slowly. These patterns suggest continuity rather than repeated technological interruption. Importantly, silence does not mean impossibility. It means that nothing we have observed so far requires extraordinary explanation. Natural processes, complex and powerful as they are, account for what the rocks show us. This perspective encourages humility. It reminds us that Earth does not owe us a complete record. The planet preserves what it can and forgets the rest. Our interpretations must remain proportional to the evidence available. Silence also invites reflection. It highlights how unusual our current moment is. For billions of years, Earth systems operated without conscious technological direction. Now, in a brief span, one species has begun to influence those systems deliberately and globally. The rocks of the future will not be silent about this period. They will carry our signal forward, even after names, languages, and structures are gone. That contrast between deep silence and sudden noise places human civilization into sharp context. As we move into the final sections, the focus will shift from detection to meaning, not meaning in a philosophical sense, but in a scientific one. What Earth's long history teaches us about continuity, fragility, and our place within deep time. Viewed across deep time, Earth can be understood as a long-running experiment in complexity. Not an experiment with intention, but one governed by physical laws, chemical interactions, and biological adaptation. Over billions of years, the planet has tested countless combinations of atmosphere, climate, and life. Most of these combinations were temporary. Conditions shifted, feedback loops changed direction, ecosystems reorganized. Some arrangements lasted only a few million years, others persisted far longer. Through it all, Earth continued, adjusting quietly to each new configuration. Life itself has been the most influential variable. From single-celled organisms to complex ecosystems, living systems have altered Earth's chemistry, surface, and energy flows. Oxygen transformed the atmosphere, plants reshaped land and soil. Animals redistributed nutrients. None of this required technology. It emerged naturally from biology interacting with environment. What makes this perspective useful is that it removes human exceptionalism without diminishing human significance. Humans did not interrupt a static world. We entered a system that has always been dynamic, always responsive, always capable of change. In this sense, Earth has hosted many experiments before us. Some involved new metabolic pathways, others involved new body plans. Some reshaped climate, some ended abruptly. Each left a trace, however faint, and then made room for something else. Human civilization represents a new kind of experiment, one that operates through conscious planning and external energy use. It is not the first system to alter Earth globally, but it is the first to do so intentionally and rapidly. Understanding Earth as an ongoing experiment brings calm to the question of past civilizations. It suggests that the planet has explored many possibilities, most of which left no lasting technological signature. It also suggests that novelty does not require repetition. Some outcomes happen once. This perspective widens the lens. Instead of focusing on what might be hidden, it emphasizes what is continuous. A planet capable of change, resilience, and renewal, regardless of which systems temporarily dominate its surface. As we continue, this long view will help place human civilization and the question of earlier ones into a broader pattern shaped by time rather than speculation. When scientists step back and look across Earth's entire history, certain patterns begin to emerge. These patterns are not precise repetitions, but recurring themes shaped by physics, chemistry, and biology, acting over immense spans of time. One of the most consistent patterns is balance, followed by disruption. Long periods of relative stability are interrupted by moments of rapid change. Climate settles into a range, ecosystems adapt, energy flows find equilibrium. Then something shifts, sometimes slowly, sometimes suddenly, and the system reorganizes. Another pattern is recovery without return. After mass extinctions or major disruptions, life does not revert to its previous form. Instead, it explores new configurations. New species arise, new relationships form. The planet moves forward, not backward. We also see limits repeated across time. Resources constrain growth. Environments impose boundaries. Systems that expand too far or too fast tend to become unstable. Whether the system is biological or geological, unchecked change eventually encounters resistance. These patterns matter because they provide context. They show that Earth does not follow a simple linear path toward greater complexity or control. Instead, complexity rises and falls, adapts and resets, always shaped by underlying constraints. When viewed through this lens, human civilization fits into a familiar structure: rapid growth, expanding energy use, increasing environmental influence. These features are not unique, even if the mechanisms are new. They echo broader dynamics seen throughout Earth's history. This does not imply inevitability. Patterns describe tendencies, not destinies, but they offer perspective. They remind us that large systems, whether ecosystems or civilizations, are subject to the same physical limits as everything else on the planet. By recognizing patterns across deep time, scientists avoid overinterpreting any single moment. They look for consistency, for context, for how individual events fit into long-term trends. As we approach the final sections, these patterns help frame a gentle transition, from examining Earth's past to understanding our present within that vast repeating rhythm. One of the quiet questions that emerges from deep time is timing. If Earth has been capable of supporting life for billions of years, why did humans and technological civilization appear so late? From a scientific perspective, the answer lies in a series of constraints that took immense time to align. Early Earth lacked oxygen. Its atmosphere was hostile to complex life. It took billions of years of biological activity before oxygen accumulated to levels that could support large, energy-demanding organisms. Even after oxygen became abundant, complexity did not accelerate immediately. Multicellular life appeared, but remained relatively simple for long periods. Stable ecosystems had to form, food webs had to deepen, energy had to become reliably available at higher levels of the biological chain. Climate stability also played a role. For much of Earth's history, conditions fluctuated dramatically. Ice ages advanced and retreated. Continents shifted. Oceans opened and closed. These changes repeatedly disrupted ecosystems, limiting how much complexity could accumulate before being reset. Humans emerged during a rare window when several factors overlapped. The climate, while variable, was relatively mild. Large mammals existed, providing high-energy food sources. Fire could be controlled. Social cooperation became advantageous. Long childhoods allowed learning to compound across generations. None of these factors alone was sufficient. Together they created an opening, narrow and temporary, in which technological intelligence could arise. This helps explain why humans appeared late, rather than early or repeatedly. From this perspective, civilization is not delayed by chance, it is delayed by requirement. Earth needed time to build the conditions that made such an outcome possible. Understanding this timing reframes the question of earlier civilizations. It suggests that even with vast time available, opportunities for technological intelligence may have been limited. Earth was not waiting, it was preparing. This realization does not diminish the wonder of human emergence, it deepens it. It shows that our presence is not inevitable, but conditional, shaped by a long sequence of prerequisites that took billions of years to assemble. When we look across Earth's history, it becomes clear that intelligence, especially the kind that leads to technology, is not a guaranteed outcome of evolution. Life can thrive, diversify, and persist for immense spans of time without ever developing complex cognition or symbolic thought. For billions of years, life on Earth consisted entirely of microorganisms. These organisms were extraordinarily successful. They transformed the atmosphere, reshaped chemistry, and formed the foundation of all later ecosystems. From an evolutionary standpoint, they did not fail. They dominated. Even after multicellular life appeared, intelligence emerged only in limited and uneven ways. Many lineages developed specialized bodies, efficient metabolism, and stable ecological roles without increasing brain complexity. For most organisms, intelligence beyond a certain level offered little advantage. Large brains are expensive. They require significant energy, long development, and social structures capable of supporting extended learning. In many environments, these costs outweigh the benefits. Evolution tends to favour solutions that work well enough, not those that are maximally complex. This explains why intelligence appears sporadically rather than steadily increasing across time. It also explains why technological intelligence, which depends on abstract reasoning, planning, and cumulative culture, appears to be even rarer. From this perspective, the emergence of human-level intelligence was not simply a matter of time passing. It required a precise combination of pressures and opportunities. Change the climate slightly, alter food availability, shorten lifespans, reduce social cooperation. Any of these shifts could have redirected evolution down a different path. Understanding that intelligence is not guaranteed helps keep expectations realistic. A long planetary history does not imply repeated civilizations. It implies many experiments, most of which never approach technology. This insight brings calm to the question we have been exploring. It reminds us that rarity does not require explanation beyond conditions. Earth may have hosted countless intelligent organisms without any of them crossing the narrow threshold into civilization. As we approach the final sections, this understanding allows us to view human civilization not as a mystery demanding repetition, but as a fragile outcome of deep time, one that exists now, briefly, within a much longer story. Science advances not by certainty, but by restraint. Especially when exploring deep time, scientists learn to move slowly, to test ideas repeatedly, and to remain comfortable with unanswered questions. This humility is not a weakness. It is what allows knowledge to grow without distortion. When evidence is limited or ambiguous, the most responsible response is patience. Deep time research rarely provides sharp conclusions. Signals are faint, records are incomplete. Multiple explanations often remain possible at once. Rather than forcing resolution, science holds these possibilities in balance. This approach is especially important when questions touch on human uniqueness. It is easy to project meaning onto gaps in the record, or to see intention where none is required. Scientific humility resists that impulse. It asks what can be supported, what remains uncertain, and where interpretation should stop. Humility also recognizes the limits of our perspective. We study Earth from within a very brief moment of its history, using tools that continue to evolve. Future discoveries may refine or revise what we think we know today. Accepting this keeps conclusions flexible rather than fixed. In the context of earlier civilizations, humility allows science to say two things at once. There is no evidence that requires such civilizations to have existed. And yet, Earth's history is vast enough that not everything can be known with confidence. Holding both ideas together keeps the discussion grounded. This balance brings calm. It removes urgency. It allows curiosity to exist without anxiety or belief. Questions remain open, but not unresolved in a troubling way. As we move toward the closing sections, this humility becomes a guide. It shapes how we return to the present moment, not with revelation, but with perspective. Seen through the lens of deep time, human civilization appears as a brief signal, sharp, intense, and recent. For billions of years, Earth changed slowly. Then, within a few centuries, atmospheric chemistry shifted, ecosystems reorganized, and new materials spread across the planet. This contrast is striking. Our impact is not large because we are many, but because our energy use is concentrated and amplified. We move carbon quickly, we redirect water systems, we alter landscapes faster than natural processes typically do. From a geological standpoint, this makes our era unusual, not unprecedented, but rare. Few moments in Earth's history show such rapid global change without an external trigger, like an impact or massive volcanism. This realization does not imply permanence. Signals fade, layers compress, even strong markers eventually blend into background variation. But for now, our presence is loud in geological terms. Understanding ourselves as a signal rather than a centre brings clarity. It places human civilization alongside other brief but influential moments in Earth's past. It also reminds us that duration is not guaranteed. This perspective is not meant to judge, it is meant to situate. We are part of Earth's record now, not separate from it. Our actions are being written quietly into layers that will outlast us. As we move toward the end, this understanding helps us return gently, from deep time back to the present, carrying perspective rather than conclusions. At the beginning, we noticed how old Earth is, and how small human history appears by comparison. That contrast has guided everything since, not toward answers, but toward scale. We explored what Earth preserves and what it erases. We looked at intelligence, energy, and time. We saw how rare technology is, and how easily its traces can fade. We learned why silence in the rocks is expected, not mysterious. Returning to the opening thought, the question remains gentle, not did a civilization exist before us, but what does Earth's long memory allow us to know? The answer is quiet. Earth remembers patterns, not stories. It records consequences, not intentions. It preserves change when that change reaches planetary scale. This understanding does not close curiosity. It refines it. It allows wonder without expectation and uncertainty without discomfort. Not knowing everything is not a failure of understanding. It is a natural outcome of studying a world shaped by billions of years of change. Some details will always be lost. Some questions will remain open. Science accepts this calmly. It continues to measure, compare, and refine. It does not require final answers to remain meaningful. In many ways, uncertainty is what keeps inquiry alive. For listeners now resting, this acceptance mirrors something familiar. Thoughts do not need resolution to settle. Questions do not need answers to quiet the mind. Earth continues whether or not it is fully understood. Layers form, processes repeat, life adapts. The planet does not hurry. In this wide context, human curiosity becomes part of the flow, not separate from it. Earth has moved through fire, ice, growth, and loss. Long before humans and long after us, it continues. Layer by layer, moment by moment, it carries forward what can be carried and releases the rest. Nothing needs to be resolved tonight. The planet is patient. Time is wide. Understanding arrives slowly when it arrives at all. Everything flows. Sleep in that motion.